Hello everyone. In this video we shall cover the subtopic 5.5 covering entropy and spontaneity. In video number 1 I will discuss the concept of entropy, while in video number 2 to follow I will discuss the concept of spontaneity of a chemical reaction. Entropy is defined in the new syllabus as a measure of how the available energy is distributed among particles in a system. The units of which are measured in joules per mole Kelvin. The old definition, which is a more clearer definition, a less in-depth definition, is defined as entropy is a measure of the disorderliness of a system. You can think of disorder in terms of the particles in the system in different states, such as solids, liquids, or gases. In a solid, the particles are stationary and vibrating in place, and thus the disorder is at a minimum. While on the other hand, the particles in a gas are moving with high kinetic energy, and thus the disorderliness of a system is very high, and thus the entropy is high. Thus, the higher the disorder of a system, the greater is its entropy. The new definition goes more in depth, and as I stated, it's a measure of how the available energy is distributed among particles in a system. For example, when particles in a solid are vibrating in place, there are not many ways in which the energy can be distributed among the particles in a system. The energy is only in the form of vibrational motion or vibrational energy. While on the other hand, when looking at a gas, the energy can be distributed among the particles in the system in many different ways, such as translational motion or energy, as well as rotational and vibrational. This is stated more clearly in the book, which I have placed over here. As you can see, the three states of matter: solid, liquid, and a gas. As you move from solid to liquid to a gas, the entropy increases since the disorderliness of the particles within the system increases. It is explained here in terms of how the available energy can be distributed among particles in a system, and as I stated previously, in the solid state there are not many ways in which the energy can be distributed among the particles. It's basically vibrational energy, while in a gas the energy can be distributed in many different ways, such as translational motion as well as vibrational and rotational motion. And thus there are more ways in which the energy can be distributed among the particles in a system, and thus the entropy is higher in a gas than it is in a solid, and the liquid being an intermediate. I'm going to read this paragraph from the book over here. When a system becomes more disordered, the energy in it can be distributed in more ways among the available particles, and the entropy of the system is higher. An example from a real-life situation states here to imagine 100 people sitting on chairs in a hall. There is only a limited number of ways in which they can move but still remain seated. However, if you have the same 100 people running around in the hall, there is an absolutely enormous number of different ways in which they can move. The first situation, in which they are sitting in their chairs in a hall, can be likened to a solid, and the second to a gas. In a gas, all the particles are moving at different speeds in different directions and also rotating and vibrating, and there is a huge number of ways in which the energy could be distributed among all different particles, still giving the same total energy, and thus it has very high entropy, high disorder. While in a solid, the particles are more constrained and there are fewer ways in which the energy could be distributed among the particles, and thus it has a lower entropy, and once again the liquid being an intermediate between both. Therefore, the greater the number of ways in which energy can be distributed among particles in a system, such as in a gas, the greater the disorder, and thus the greater the entropy of the system. We can think, and generally, we can think of entropy in terms of the disorderliness of a system, and thus, as I just stated, the disorder in a gas is much greater than that in a liquid, and the liquid is much greater than that in a solid. One thing to note is the units of entropy. It's in joules per mole Kelvin. While we always measure the enthalpy change of a reaction, enthalpy change of a reaction in kilojoules per mole. And as you will learn in video number 2, the Gibbs free energy change, which we will learn, is also measured in kilojoules per mole. Therefore, the only different units are for those of entropy, which are in joules per mole Kelvin, which need to be modified when using mathematical equations, as I will discuss in video number 2. Entropy, unlike enthalpy, which cannot be measured as stated in previous videos, entropy can be measured, and its value for different compounds at 298 is listed in the data booklet in table 12. The values listed are those for absolute entropy, which is defined, the absolute entropy is defined as the increase in entropy on going from 0 Kelvin to 298 Kelvin. Since you should know that at 0 Kelvin there is no energy, theoretically speaking, and thus the system is perfectly ordered. There is no energy to be distributed among particles in the system, and thus the entropy is 0. Upon heating from 0 Kelvin to any higher temperature, the entropy of the system will increase. This is stated here. At 0 Kelvin, the entropy of a system is 0, since energy is 0 at 0 Kelvin, and the system is perfectly ordered. Upon heating from 0 Kelvin, particles gain energy, and thus disorder increases, and the ways in which the available energy can be distributed among particles in a system increases as well, and thus the entropy increases. The absolute entropy values of many compounds have been measured and listed in table 12 of the data booklet, all of which are positive values, which indicates an increase in entropy on going from 0 Kelvin to 298 Kelvin, but to differing degrees depending on the compound under study. As you can see here, I've represented table 12 from the data booklet for many different compounds, as you can see here, and the absolute entropy values in joules per mole Kelvin are listed here, all of which are positive values, because as stated, entropy increases on going from 0 Kelvin to any higher temperature, and the temperature under study here is at 298 Kelvin. Thus, these values represent the increase in entropy of these molecules on going from 0 Kelvin to 298 Kelvin, and thus all are listed as positive values. This is the entropy, not the entropy change of a reaction, and thus the entropy can be measured. The entropy change of a reaction can also be calculated, which is represented by delta S. The symbol of entropy is S, and the absolute entropy is S standard, while the entropy change of a reaction is delta S standard, as listed here. To calculate the entropy change in a chemical reaction, we can use this general rule here. The entropy change of a reaction is the difference between the entropy, the sum of the entropy of products minus the sum of the entropy of the reactants, as displayed here. Thus, if a chemical reaction takes place and there is an increase in entropy, that means the entropy of the products is greater than that of the reactants, which will produce a positive entropy change for the reaction. Thus, an increase in entropy, as stated here, in a chemical reaction produces a positive entropy change of reaction, since the absolute entropy of products is greater than that of the reactants, and once subtracted, this will produce a positive value. And thus, if a reaction is accompanied by an increase in entropy, the delta S of the reaction, the entropy change of the reaction, would produce a positive value. On the other hand, if a chemical reaction is accompanied by a decrease in entropy, as stated here, a decrease in entropy in a chemical reaction produces a negative entropy change of a reaction, since the absolute entropy of the products will be lower than that of the reactants, and once subtracted, the entropy change of the reaction would be a negative value. Thus, one can predict the sign of the entropy change of a reaction without even calculations, without conducting calculations, and thus this is an excellent way to check your answer after calculation. If you expect a chemical reaction to have an increase in entropy, as we will cover in the next section, then the entropy change of the reaction should be a positive value once calculated, and vice versa. One can easily predict the sign of the entropy change of a reaction using the following rules that I've listed over here. in this section, predicting the sign of entropy changes. You can predict the sign of the entropy change of a reaction in terms of the states of matter of both the reactants and products when comparing them together. Thus, if a substance changes from a solid to a liquid, the entropy value increases, or the entropy change increases, and thus the entropy change produced would be a positive value. If the substance changes from liquid to a gas, then the entropy would increase as well, producing a positive entropy change of reaction, since the entropy in the products, which are the gases, is higher than that in the entropy of the reactants, which are a liquid. The same applies when a substance changes from a solid to a gas. The absolute entropy of the products, which are in the gaseous state, would be higher than that of the reactants, which are in the solid state, and once subtracted, this would produce a positive value as well. Thus, one should note the state symbols of both reactants and products in order to predict the changes in entropy in a chemical reaction. I will cover examples of this in the worksheet. Another rule for predicting entropy changes of a reaction: any reaction producing a gas will increase the entropy of the system. Thus, I've placed an example here. If the reactants are both in the solid and aqueous state, while in the products, all the products are in the aqueous liquid, and one of which, the CO2 gas, is in the gaseous state. The entropy in the gaseous state for molecules in the gaseous state is the highest, and therefore the entropy in the reactants here would be expected to be much lower than that in the product, since we have a gaseous product in the gaseous state over here, and thus the entropy change of the reaction would be positive. If this were written in the opposite direction, the entropy change of the reaction would be negative. The third rule for predicting entropy change of reactions, the sign of the entropy change of reaction, discusses that involving reactants and products that are both in the gaseous state, or if there's molecules in the gaseous state in both the reactants and products. The way to do this is to check the number of moles of gaseous molecules in both the reactants and products. Thus, an increase in the number of gaseous moles in a chemical reaction increases the entropy of the system, and the delta S, or the entropy change of the reaction produced, would be a positive value. Since if there is a higher number of moles of molecules in the gaseous state in the products, then the entropy in the products would be higher than that in the reactants, and the entropy change of the reaction produced would be a positive value. I've placed an example here: the reaction of nitrogen with 3 moles of hydrogen gas to produce 2 moles of ammonia gaseous molecules. All the reactants and products are both in the gaseous state, and thus to decide whether the entropy change is a positive or negative value, whether it decreases or increases, one should check the number of gaseous moles. Thus, in the reactants here, we have 4 moles of gas. As the reaction produces products, we have 2 moles of gas in the products, and therefore the number of gaseous moles decreases, and thus the entropy the entropy would decrease during this chemical reaction, and thus the entropy change, which is the sum of the entropy, the absolute entropy of the products subtracted from the sum of the absolute entropy of the reactants, would produce a negative value in this case. If the arrow was written in the opposite direction, in this direction, then there would be an increase in the number of gaseous moles, and thus the entropy change would be a positive value. Therefore, an increase in entropy is always represented, an entropy in a chemical reaction would always produce a positive value for the entropy change of the reaction, while a decrease in entropy during a chemical reaction is always represented using a negative value for the entropy change of a reaction, as in this example over here. We are required to calculate the entropy change of chemical reactions using the general equation over here, which is the entropy change of a reaction is the sum of the absolute entropy values of products subtracted from the sum of the absolute entropy values of reactants, which are listed in table 12 of the data booklet, or sometimes they are listed in the question given in the exam. I've placed an example here. which asks to calculate the standard entropy change of the following reaction, which is the same reaction that we covered previously. We predicted the sign of this entropy change to be negative since the number of moles of gaseous moles decreases in this reaction, and thus the entropy decreases, producing a negative entropy change of reaction. Once we calculate this value, it should produce a negative value for this entropy change. Thus, using the rule, I've listed here the absolute entropy values of both the reactants and products in joules per mole Kelvin. The absolute entropy value for N2 per mole of N2 is positive 192. The absolute entropy for hydrogen in the gaseous state per mole of hydrogen is positive 131, and the absolute entropy value in joules per mole Kelvin per mole of ammonia is positive 193. As I stated, all these values would be positive values because they are absolute entropy values. And thus, to calculate the entropy change of a reaction, we would sum the absolute entropy values of the products and subtract from it the sum of the entropy of the absolute entropy values of the reactants, producing the following mathematical equation. Therefore, the sum of the entropy of the absolute entropy of the products, which are ammonia, in this case ammonia in the gaseous state, is positive 193 multiplied by 2, since we have 2 moles of ammonia in this case. Thus, this would equate to 2 multiplied by positive 193. And then I would subtract it from the sum of the absolute entropy values of the reactants, which are nitrogen and 3 moles of hydrogen. The absolute entropy value for nitrogen is positive 192. So positive 192 plus 3 multiplied by the absolute entropy of hydrogen, because the absolute entropy is per mole, and I have 3 moles of hydrogen in this case and 1 mole of nitrogen. This is why this was kept as 192 over here, plus 3 multiplied by positive 131. If you were to calculate this value, this would produce a negative value for this entropy change of the reaction, since the number of gaseous moles decrease. The next concept is asked frequently in multiple choice questions on exams. Therefore, I will discuss it here. For when considering an exothermic reaction, energy is transferred from the system to the surroundings, and thus the amount of energy in the system decreases while the amount of energy in the surroundings increases, and thus the number of ways in which energy can be distributed among particles in the system decreases, meaning the entropy decreases, and thus the system becomes more ordered, and thus the entropy decreases, while the surroundings gain energy, and thus the number of ways in which the energy can be distributed among particles in the surroundings increases, meaning entropy will increase, which I've stated here. For an exothermic reaction, since energy is transferred from the system to the surroundings, the entropy change of the system decreases. Basically, it would produce a negative value for the system, while the entropy change of the surroundings increases, forming a positive value for the entropy change of the surroundings, and vice versa. For an endothermic reaction, since energy is transferred to the system from the surroundings, the entropy change of the system increases. Thus, the system's entropy change would produce a positive value, while the entropy change of the surroundings decreases, and the entropy change of the surroundings would produce a negative value in this case. This covers the topic of entropy, which will be used to calculate the spontaneity of chemical reactions in video number 2. Please move on to watch video number 2, and thank you for watching.